So, my name is Brandon. We're part of Team 1466, Webb Robotics, and we'll be talking about composite materials in FRC. You want to introduce yourself?
Oh yeah, I'm Sam.
And I'm Alex.
All right.
So, founded in 2004, Webb Robotics has been putting an emphasis on community service and like STEM outreach, and that includes today, which is our Composites project, and we'll talk about how you guys can get involved later. Alright, so it first started with the SAMPE Foundation 2 years ago, summer of 2024, and it's particularly focused on bringing composites to robotics and teams in robotics. So our initial goal is to create lessons and kits used by teams around the world to be out later this year.
Alright, so what is a composite? A composite is a material made out of two different things, a matrix and a reinforcement. So the matrix can be made out of stuff like, carbon, fiber, if you've heard of fiberglass and carbon fiber. That's what the base of the material is. It's called a matrix, and they're weaved together. And then there's some sort of resin or hardener that goes on top of them called a reinforcement. And the idea with these composites is that when the two materials are combined, they have stronger properties and better properties than individually. Kind of a 1 + 1 = 3 idea. Right, so these are weaved together in different sort of ways that we're going to talk about later. And then the reinforcement is put on them, and they're super strong and super light compared to other building materials like aluminum and steel.
Alright, so why would you use a composite? Obviously, we have strength. It has a very high strength-to-weight ratio, better tensile strength, and resistance to everything you might encounter on the field. It can do tasks traditional materials cannot, and a good example of that would be on our bot. We had an arm that was extra strong because we used composites, and we'll get into that later. But my favorite reason of why we use composites is because it looks cool. So, why industries use composites? Obviously for the same advantages that Brandon just spoke about, but particularly that high weight to strength ratio, like we see here. It's very strong, and it doesn't break. But we see it. That's why we see composites and like carbon fiber being used so much in extreme sports like racing or mountain biking. It has customizable, tunable properties, which means you can mix different matrices and reinforcements together to get the properties you want. So a good example of that is like the weave patterns you have on your carbon fiber can change like the flexibility in certain ways. And then telescoping arms and climbers, things that weight is a necessity to be light, is particularly important. And strong plastic, lighter than metal, and minimal loss of strength compared to aluminum. So where we use composites in our team, like Brandon had just mentioned, we had an arm on a robot as seen here, and you guys can just like pass this around and test how strong it is. It did us really well. It never broke throughout the season, and it was able to hold all that weight of like the motors and coral and the strain and without breaking. We also used this. We actually made in-house ourselves, and we vacuum bagged and fused it, and then used it to a CNC to cut it out. But we also used carbon fiber just from shipping and off-the-shelf parts that we put on our side paneling as well. So these are some common types of composites. So we have our Kevlar, the stuff in bulletproof vests, carbon fiber, which is one of the most applicable in robotics, fiberglass, which most teams use already, and Rice Krispie treats, which we all eat. And these are the finished products of each of those applications.
All right, so when should you use composites on your robots? So the great thing about composites is not only they're strong, they're light. So you want to use them on mechanisms toward the top of your robot to really prevent your robot from being top heavy. As you can see, last year what we did is on our coral intake, we had our plates for carbon fiber there, which actually reduced a lot of weight. You also don't want carbon fiber in high contact parts because while it's very strong and breaks very, seldom, when it does break, it's kind of a pain to repair. So you want to use carbon fiber and composites in places that don't break very much. And as Alex and Brandon said earlier, when you want to do something cool, it's a great, way to stand out from other teams.
So here's some terminology that we'll be using throughout the presentation. So a toe is, as you guys can see on the carbon fiber things, it's that little rectangle that goes in one direction. A crimp is when they cross over to each other. Stability is the ability to maintain orientation laid over 3D. And a weave is the orientation, so you can get different things from different weaves. Alright, so the purpose of a weave, it determines its characteristics, like I said. Composites can be very customizable, and it can be altered and enhanced depending on the type of weave material. So, for example, would be this weave we have right here is very good at being pulled, but not as good at compression. So you can choose those customizable things depending on your weave. Patterns change mechanical properties of the composites, and weaves affect things like load strength and tensile strength based on the individual fibers and how they distribute the force over that entire surface. So you can pass that along.
All right, so some different types of weaves. You get the plain one, which is very simple. You just, move the fibers over and under each other like a checkerboard. And it's great if you want a one-dimensional or two-dimensional plate, but it's not great once you have to start, contouring shapes, right, and making them three-dimensional. So twills and satins are other types of weaves we use to kind of counteract that and make them 3D. They both have pretty good pliability. The satin weave doesn't have as much stability as the other one, but it's easy to shape into 3 dimensions. The unidirectional one is kind of a fun one, and it's very, very strong in one direction, right? Because all the fibers are going the same direction. Obviously, it's not that commonly used because of the obvious problem that it's really strong in one direction, but not that strong in another direction.
So different weave patterns can also get your desired, what you want from a composite. So here are just some couple of the weave patterns of the plain weave that we talked about all around, the twills and this everything. So those are just some weaves. So reinforcement fibers, like I mentioned before, they can be varied in many different ways: material length, weave pattern, thickness, and they can be divided in different categories. So we have carbon fibers, glass fibers, boron fibers, ceramic, metal, and natural. And these all have different types of properties and behaviors. Strength, weight, tensile, they all have different properties. But you also need to be careful when working with composites because they are irritable to the skin, so you have to use gloves and to not get fiber into your skin. So, how does a reinforcement work? So the reinforcement is what actually is holding the main load together, but it's really the matrix and the reinforcement together, put together, which gives the composites that strong and tensile strength. So as we can see on that image over there, they're laying it over in different directions, so it is strong in every direction. And on this one, this is matrix only. It's clear that it's a lot of crack, and composite, it spreads out throughout the entire thing. So instead of just being on one point, it's on the entire panel, which gives it that strength. So your matrix polymer is your binding agent between them, and it's what holds the polymers together. It helps redistribute the force evenly, and it has a strength, shelf life, and low weight. The only downside to this is it's very expensive sometimes, and it can be an exothermic reaction when you're applying it to like carbon fiber. So you have to be careful with like safety when you're working with like epoxy resins. Vinyl ester and polyester are also alternatives, but they have their own uses and weaknesses. So here are some types of resins that we use. This is safety warnings to wear safety glasses and how these chemical reactions can be dangerous and should be handled appropriately, so we'll get into that later. Go on to the next slide. This is the resin that we use for making our own carbon fiber. So it's a slightly higher cost, but it's higher strength and a long shelf life, and is very good with carbon fiber. So this is what we'll be doing. This is what we have done with our team for making our own carbon fiber plates. And so what we do is we have our epoxy resin curing, and we cut our carbon fiber, and we use the vacuum infusion method. So what we do is we put it on a panel, and it will come out something like this, and the resin will shoot through on both ends and come through and make that awesome carbon fiber shiny look. And this is something that we plan to do with y'all in the future, and we will get into that later. This is, for anyone concerned, these are safety basics. So this is Lucas, one of our team members. He showed up to one of our without closed-toed shoes, and we did not let him continue, even with him trying to put gloves on his feet and make them closed-toed.
All right, so what should you be wearing in a lab with composites? And some important things to note here is with the fiber, you're dealing with a bajillion tiny needles that can go into your skin, and the resins are often irritants. So my way of thinking about this is cover as much of your body as you can. Obviously, you want gloves, you want face coverings, you want goggles, but I always like to wear like long sleeve shirts, like you can see that Becca's doing there. The first time I made a composite, I put the part of the composite, the fiber that kind of looks like a Chinese finger trap, I put it on my arm, and my arm hurt for a long time because it's just a lot of needles going into your skin. So don't put those around your arm. Cover as much of your body as possible. Obviously wear closed-toed shoes. And when you're cutting the carbon fiber, it can be pretty loud, so make sure you wear your protection as well.
Alright, machining considerations for carbon fibers. They're weak to heat, and the thermal stability depends on like your matrix. We typically use CNC milling out of house. But it requires specific settings, router, and spindle speeds. There's also water jet cutting, which is really good for composites because it's able to collect that dust as you're cutting it as well. And then it has fast, dependable cuts. For sandwiched composites, high RPM is definitely needed. So like carbon fiber and honeycomb, we have different like levels of that sandwich. So the arm we had passed around earlier was about 5 layers of carbon fiber, while like this side paneling plate right here is around 8, and it's much more like robust. Yeah, so you can pass that around. So if you don't want to make your own composites or carbon fiber, here are some just vendors that can sell them. Next slide. So here's some vendors that are known for FRC and are good at making carbon fiber that we have used in previous years. And if Alex, the ACE cutting edge course, if you want to learn more about like CNC and carbon fiber composites, it's a great resource for beginning machinists. It's around like 4 hours of coursework with a certification, and it has tons of other amazing opportunities. So we have a QR code for all those who are interested in that.
Oh, yeah.
When machining it, do you need to wear a mask because of the needle particles?
Yeah, the dust can be very, you don't want to inhale it, so a mask is recommended, but if you're using like a water jet, it's able to collect the dust. Still wear a mask, but you'll be less susceptible to it.
And I'll just add ACE is free.
Yep.
Yeah, absolutely. So the SAMPE Foundation has some great resources if you want to learn more and try to make composites. We have this textbook that we're going to hand out to the teams called Composites, Lighter, Stronger, Better, which is by Brent Strong, and they have a great YouTube channel with some videos that are linked here. We'll send the slideshow out so you can watch the videos later, and you can learn a lot, not only about how to make composites, but how they can improve everyday society, what they can be used for, what they can't be used for, and just how they can make the world a better place.
So we strongly recommend you guys take a look at this textbook and take one home with you. So this is now the point of the slideshow where we can tell you how to get involved in making composites. We will be holding workshops at our robotics lab later on in the season and teaching you guys how to make your own composites. And later on we plan to send teams composite kits to actually make their own composites and design your robot with composites, because it's just the next steps forward. So here are some links for you guys to use. The slideshow link, I strongly recommend you guys take a look back at that if you're interested in learning with us and how to make composites and carbon fiber and other resources. So next slide. Yeah, thank y'all. Do you have any questions?
Yeah, when you want to make a part that's thick, okay, do you just make a thick plate and then cut it out so you end up with like a racket handle or something, or do you wrap it in a way that you make the whole part at one time without any later milling?
Yeah, exactly. So if you want to make a part that's extra thick, you can use and put things in between. Kevlar off. Composites. So this is like a cardboard type mesh between the composites to make it a little bit extra thick without using those expensive carbon fiber layers. So you can put stuff in between the carbon fiber on both layers, and it's the carbon fiber on both sides that'll give it that strength.
Now I want to cut a tennis racket shaft in half and see how they do.
Yeah.
They actually make some tennis rackets out of carbon fiber. They
Right.
use the.
I'm just wondering how they did that, how they got the thickness, from a procedural point of view.
Yeah, so a lot of the times what they do is they have like a mold, and then they use something called wet layering. So we did that with Kevlar here. We made like a piece where we put a mold around it, and then we have a 3D printed part in there. So has like all of the protection of Kevlar, but it's around a mold.
So it's like a shell.
Yeah, it's like a shell.
Okay.
Just like the cardboard is to the
I
carbon
always
fiber.
wondered about that.
Yeah.
Do you all generally manufacture the composites, then cut them, or cut them, then manufacture? Then
So what we get is we get the carbon fiber weave, and then we put epoxy resin on them and vacuum infuse them, and it comes out with a fully finished plate. So is that answer what you're asking? Yeah. So once we make our plates, we'll then manufacture like a big plate, and then we'll cut out the piece we want with it. So here was like an early model design that we were wanting, and then we cut this out from CNC from a larger plate. Composites and carbon fiber should be your last design step, not your first. You shouldn't design and make products of your first iteration with carbon fiber. It's too expensive.
Is it pretty much impossible to make one of these laminates that are transparent?
A carbon fiber laminate that's transparent?
Yeah. Pretty much impossible.
I think it is, because you have your reinforcement in your matrix, and your matrix is going to block any transparency through the carbon fiber. But you could use things like plexiglass or other fiberglass or other composites to make it transparent, but carbon fiber wouldn't be played. Yeah, the question.
Does wood count as a composite?
I think wood can count as a composite when you add it to other things. So if you chop it up and put it together with a resin that you see at construction sites, then that would be a composite. But just straight wood is its own. Yeah, if it has a reinforcement and a matrix, it's a composite. I strongly recommend for everybody in this room to complete our questionnaire, just to gauge interest. And Anybody who wants the textbook or take a look at it can see us after the presentation. Yep.
In your opinion, is it better to make the carbon fiber part in-house or get?
I think it's better to make it in-house because you're able to choose that layering option of how many layers you want to do. So like your weight to strength ratio is completely customizable. Your weave's completely customizable versus like an off-the-shelf part where it can typically be way more expensive than just buying the carbon fiber yourself and just making it in-house and manufacturing it. It's way more customizable and it's way cheaper.
How much money do you think you guys spend on this, like roughly like per build season? And then is it like worth the
So that's exactly where the SAMPE Foundation comes in. So we've gotten a grant and they give us the materials, everything, and teach us how to make our composites. And we'll be teaching other teams who are interested in composites or want to sign up for this, and we'll give them kits and materials, so it covers a lot of the cost with these kits. And if you want to spend more money on composites and further learn about it, you can by buying materials later, but we strongly recommend get the kits first. So the only real cost for us is time, because we make most of our carbon fiber pieces, and the off-the-shelf parts, they don't come too expensive, but it's just better to make them in-house. Yeah.
What would you say is like the average turnaround time with something that's like 8 layers thick, or pretty thick stuff?
So they're about the same time. So when we vacuum bag something, the amount of layers you put on doesn't really affect the time. So we just leave it vacuum infusing overnight for like 24 hours, and that's typically enough for the resin to harden and the layers to be solidified.
What part of the robot do you feel you get the best bang for your buck with composites?
Okay. So we like to use it generally as like a plate because it's really light, and like towards the top of our robot because it's pretty light, and you know, like in past when you have like telescoping mechanisms, this stuff that goes really high, it's nice to use carbon fiber parts up there because they're light and you don't have to worry about the robot being too top heavy.
Places where mechanical bench isn't really on your side. I wouldn't really recommend you put them on like the base of your bot or somewhere it might get broken easily because they are expensive and you can't really repair them. It's really a one-time thing. So if I were to break this plate, then I would have to remake another plate to replace it. So choose wisely. Yeah, you can't weld it back together like you could with metals or something like that. Once it's broken forever. Any other questions? Well, thank you, and please fill out our questionnaire.